picking up good vibrations.
We can use the DFT, Discrete-Fourier Transform, to compute a discrete convolution of two signals. And this is one of the main uses of the Discrete-Fourier Transform. While the procedure to compute the convolution involves a set of trivial steps, to fully understand it is subtle. This video explains these steps and these subtleties.
Let us say that we have a signal x of n depicted in blue and a signal h of n depicted in orange, and we want to compute the convolution, which we denote by y of n. We can follow the standard procedure that we have learned and that is illustrated in the animation, and we obtain the signal y of n depicted in green at the bottom. One very important fact is that if x has length capital N and h has length capital M, then y has length capital L equals capital M plus capital N minus 1. However, we want to arrive at this very same result, y of n, using the DFT. Recall that conceptually we can compute this convolution with the following procedure. We can compute the discrete time Fourier transforms of x and y leading to signals capital X and capital Y, which are depicted on the right hand side just for illustration. With this I mean they do not correspond to true discrete time Fourier transforms of x and y, but are depicted rectangles and triangles just for illustration. After computing these discrete time Fourier transforms of x and y, depicted in blue and orange, we multiply the two, leading to the green discrete time Fourier transform at the bottom right. Then we compute the inverse Fourier transform and obtain the result of the convolution in discrete time denoted by y of n. However, this is often impossible to carry out analytically, as we cannot store the discrete time Fourier transforms in our computer. So the question is now, can we do this with the discrete Fourier transform? And if, in fact, we can do this and obtain the result of convolution with a discrete Fourier transform, what is the procedure to do so? To obtain y of n from its samples of the discrete time Fourier transform, we need to at least capital L samples, since the length of y is capital L, which is equal to capital N plus capital M minus 1. We can take these capital L samples at 2 pi over capital L times k, where k goes from 0 until capital L minus 1, as depicted on the bottom right. Since we know that the discrete time Fourier transform of y of n, denoted by capital Y, is the multiplication of capital H and capital X, which are the discrete time Fourier transforms of H and X respectively, then to evaluate y at these points of interest, it suffices to evaluate capital H and capital X at these very same points of interest. For this, we need capital L samples of capital X and of capital H at times 2 pi over capital L times k, where k goes from 0 until capital L minus 1. The procedure is also summarized here at the bottom. The capital L samples of the discrete time Fourier transform of capital X and capital H are nothing more than the capital L values of the discrete Fourier transform. Thus, this procedure can be summarized as follows. Given signals x and n of length capital N and capital M, to take the convolution of x and h, we have to compute the discrete Fourier transforms of x and h at capital L points, multiply the two, leading to the discrete Fourier transform of x with length capital L equals capital M plus capital N minus 1, and then take the inverse discrete Fourier transform and obtain the result of the convolution, which is y of n. Now, how do we obtain capital L samples of the two signals x and h of their discrete time Fourier transforms? We need to pair these two signals x and h with zeros until the paired signals have length capital L. And we need to take the usual discrete Fourier transform of the paired signals. What if we want to obtain more samples of the discrete time Fourier transform of the convolution, say, to have a more trustworthy representation? We can follow the exact same procedure, but with the desired number of samples, say capital L bar larger than the minimum number, capital L equals capital N plus capital M minus 1. In this case, we need to pad the signals x and y with zeros so that they have length capital L bar.
Let us summarize the procedure to compute the convolution of two signals. The input signal with length capital N and the impulse response with length capital M. Say that capital L equals capital M plus capital N minus 1. First step is to compute the DFT of the impulse signal with capital L samples. Second step, compute the DFT of the impulse response with capital L samples. Third step, multiply the two. Fourth step, compute the inverse DFT.
Let us now see how to apply the procedure to compute convolution using the DFTs that we have just discussed, but now using MATLAB. We'll pick two arbitrary signals, x and h. The way we define these signals is by simply defining vectors for each, and we can assign the meaning that they start at 0. For instance, vector h is equal to 1 minus 1, 2. And this means that the signal h of n is equal to 1 when n equals 0, to minus 1 when n equals 1, and to 2 when n equals 2. If we compute the convolution, we obtain a signal corresponding to this vector, 5 minus 1, 9, 7, 5, 3, 2. Let us use this result to confirm what we will obtain now using the Discrete-Fourier Transform method. So we start by defining capital M and capital N to be the length of signals x and h respectively, and then we define capital L to be capital M plus capital N minus 1. Now, this capital L is the minimum number of samples of the discrete time Fourier transform of the product of the discrete time Fourier transforms of x and h, and is the minimum number that allows us to recover the resulting convolution. So what we'll do is that we're going to pad the signal x with some zeros so that it has length capital L, and the way to do this is that initially x has length capital M, so we're going to pad it with capital L minus capital M zeros, and we're going to do the same for signal h. We're going to have padded with zeros, capital L minus capital N zeros, so that it has length capital M as well. I'm going to take the Fourier transform of the padded signal x. We're going to take the Fourier transform of the padded signal h, or actually the corresponding vectors, of course. These are the inputs to the FFT. We're going to take the product. Now it's very convenient to use this product dot star because it really computes what we want, which is a pointwise multiplication between the vectors fx and fy, and then we take the inverse Fourier transform. The instruction to do this is the IFFT. Let us now run this, and we obtain exactly the same values as before. Now, what happens if we increase n? We can always increase n. And let's say that we now consider the minimum value plus 2. Let's run this again. And what we get is a vector of length 9, because if we give a vector of length 9, which is capital L, to the FFT, both x and h underscore have now length capital 9, we also get vectors of length capital 9, and also when we invert it, we also get a vector of length 9. And then we get the same initially the 7 first samples, the 7 first values of this resulting convolution are equal to the ones we got with the conv.m instruction, and the resulting convolution is padded with zeros. What happens if we do it with less? In this case, since we go below the minimum number, we get something different. So this confirms that the minimum number of samples that we need is capital L. We cannot go below that.